Welcome to C++ Coroutines from scratch. I am Phil Nash, developer advocate at Sonar. Now, if you don't know Sonar, we do static analysis tools. We help you to write clean code. I'd love to talk to you more about that, but that's not what this talk's about. So do feel free to catch me after. Be here today and tomorrow. At least today I'm wearing this bright red SolarLint t-shirt, so I'm hard to miss. But we're going to be talking about coroutines today. And before we get to that, I want to actually get to know you a bit more as well too, particularly with respect to coroutines. So I want to ask some questions. First of all, who here in the room considers himself an expert at C++ coroutines? I'm not seeing any hands, which is quite right. It's a trick question. There's probably, I can count them in the world on one hand and still have some fingers left. And I don't think any of them are in the room today. So let's lower the bar a bit. Who considers himself at least comfortable with C++ coroutines? Maybe you've used them on a real project, or you feel confident that you probably could. So just a couple of hands, I think, if I got that right. All right. This one hopefully will get a lot more people. Who here has seen at least one other talk on coroutines and still doesn't get it? Right, most of the room. Okay, good. We've got the right crowd. So why is that? Well, I mean, it is a complex subject to start with. It's not rocket science, but it's fairly complex and a bit unfamiliar to the way we work. But then that's compounded by the way C++ does coroutines, which of course is a bit more complex than most other languages. And then that's even further compounded by lack of library support at the moment, and we may touch a bit on that at the end. So yeah, we've got all these strikes against us, but since it does take a few runs to actually get it, I'm going to take a slightly different approach to most other talks on coroutines you may have seen. They're all doing the right thing. So what we usually do when we're introducing a new subject, especially a complex one like coroutines, is we'll start with a very simple example, because we don't want to distract by the details of the problem. We just want to show what it is we're teaching. And that's absolutely the right thing to do. Except that there is a trade-off, and that's that you can come away feeling like we just use a really complex solution to a very simple problem. And that could be a little bit unsatisfying sometimes, even if you know why we're doing that. And you can leave you wondering, how does this actually scale to a real-world problem? So I'm going to try a bit of an experiment and start with a more complex, more real-world example. And there's clearly a risk there. This can easily backfire. It's not going to be for everyone. But the payoff, if it works, is that you should walk out of here having a better understanding of how and why coroutines work in C++, see how they apply to real-world problems, and at the very least be satisfied that they're a good match in complexity for the problem at hand. So that's what we're going to try and do, hopefully understand the risks as well. And one final warning, I've got a lot of material to cover in a short space of time. We probably won't get time for questions at the end. If so, again, please catch me afterwards or reach me on the Discord. There's a channel for this talk there. We'll go from there. Okay, so what is the problem that we're going to be discussing? As I say, it's based on my experience when I used to work on a quant team. Now, don't worry, you don't need to understand anything about finance or quantitative analytics, but I'm sort of using it as the background so that it feels a bit more real world, gives it a bit more of a real world color. So we've got lots of objects like these. You don't have to understand what any of them are. This is sort of a subset of the sorts of objects you might find in a real quant library. And in fact, of these, we're only going to directly see these ones today. Their objects don't actually do anything. They're mostly just holders of data, as we'll see. Even though you don't have to understand that, what's more interesting is the shape of how they relate to each other. So I just want to take a moment to explain that before we dig in a bit more, just so we understand the problem we're dealing with. So if we start with this first one, bond, you can see it's just got a number of data members. These are all simple value types. Some of them are primitive, some of them are more custom types, but they're all value types. So this is a nice, easy one. It's what we'll call a leaf object, because it doesn't have any dependencies on anything else. You can just load all the data at once. Because that's what we're going to be doing here. The problem is, how do we load these objects in from a database, or as we're going to do, the file system, or maybe from live data, and how do we deserialize that into these objects when there are dependencies at play? Now, another thing to notice here, and this is, or at least was, quite common in quant libraries when I was working on them, but you can see it's derived from f-object. It's just a name I came up with for a singularly rooted base class object. So nothing fancy there, it's just traditional OO. It's very common in quant libraries, even if it's not particularly modern. So if you see that, that's what that is. We also have further derived types. We've got fixed rate bond here, which is a bond but has some extra members. Again, nothing complex yet. Now, if we look at another type, forward in this case, again, you can see it's got loads of data members, but there's two at the end that I want to draw attention to. These two discount curve objects. First thing to see there is that PTR. Don't let that distract you. That's just a type alias for shared pointer, just because we use it a lot, so it's nice to have a shorthand. That's all that is. And then the curve type itself. This is, again, it's another polymorphic base class. Well, it's sort of more like a branch in the polymorphic hierarchy, because everything derives from f-object. So you've got this family of curve objects. And here in full, we don't know which ones they are, because it could be some different concrete type. Again, standard OO polymorphism in old school C++. So we've got flat forward and fixed rate bond forward in our example. Sorry, fitted bond discount curve, reading the wrong slide. The fixed rate bond forward is actually derived from forward, adds another dependency, in this case the fixed rate bond. Not really anything different to that. Now, we want to load it from JSON like this. So most of these are just simple value types, but we've got those dependencies in there. And you notice this convention, we've got this sort of type name, slash, and then some other numeric identifier. That's just how we refer to the data. I borrowed that convention from the real project that I worked on again. Gives it a bit of a real world flavor. Now you can see there the curves at the bottom. We've got curve slash 3, curve slash 4. When you load that, you're going to get a little bit of JSON like this. Just tells you what the actual instance is. In this case, fitted bond discount curve. So you then have to do another hop to load some more JSON for the actual type. So that's why that's a bit interesting. OK, so what we're going to do is we're going to try and load these two objects. Fixed rate bond forward 1, fixed rate bond forward 2. In doing so, we're going to have to build up this object graph. You can see you've got 10 different objects there, although the 3 curve objects, they don't make it into the final object graph. They're just there to load the actual types. So it's only 7. But we have to load these 10 objects. How are we going to do that? So let's look at some actual code. Let's say we're not going to get to coroutines yet. I'm going to start with the simplest possible thing. So I'm going to switch my mirroring over and go to a code base. Now, I hope you can read this, especially if you're further back. I did try to set a good font size. Everyone read it OK? I see hands going up. I don't know what that means. That means it's OK, good. Right. So this is our main function. It's going to be the same main in all of the examples I give you. So I'll just explain it once here. The main part is this line here in the middle, load and build objects. And then we give it those two identifiers. We call them IDs here that I just referred to on the previous slide. They're the objects we want to build, to load and build. And we'll get them back here. You can see I've got some timers going on here, just capturing start and end, so we can diff that and print out how long that actually took in milliseconds. Is milliseconds accurate enough? Well, in this case it is, and you'll see why in a little while. And then at the end, this nasty little blob. Not doing anything that fancy, it's just we know we've got a fixed rate bond forward back here, so we're casting that to this variable, and then scroll a bit, pulling out one of the members, which is our discount curve, which, as we know, is a polymorphic type, so we cast that to fitted bond discount curve. We happen to know it's that. And finally, at the end, we just assert on one of the values. And it's really just a smoke test to give us some confidence that we've actually loaded all the data we thought we had. It's by no means exhaustive, but it's sufficient for our purposes, just so we can see that's all working. So that's all we're doing here. So, of course, the interesting stuff's going on in this method. Let's look at this repo type first. Just has one data member. We're calling it a cache. So these are all the objects that we're loading, just looked up by string. That's the ID. We have this helper method here. We'll look at that in a moment. So let's look at load and build objects. So we passed in our IDs. We want to return a vector of f objects. So we know how many objects we want, so we can allocate that up front. Iterate through the IDs. And first, we'll just look up in the cache, because we've already loaded it, we've got it. And if it's there, we can put it in our output object list. Otherwise, we call our load helper. It's going to go away and load it transitively. When that comes back, we're going to put that in our output object list. And that's really all there is to it at this level. The load, all that's doing is just forwarding most of the loading onto this deserialize function, and then just puts the object in the cache. So pretty simple so far, which is great. Let's have a look at deserialize. A little bit more interesting. You can see we're loading as JSON. In a real project here, you might call out to the database or however else you're getting the data, that's where that's going to happen. This deserializer class, it's just a little convenience wrapper to give us some deserializing methods. We'll see that in action in a bit. Get type for ID. It's just up here. Just a very simple parsing operation to pull out the type name, which remember is the first part of the string before the slash. So we can use that to actually see which type we need to create. Simple type switch. Obviously, you wouldn't do this way in a real code base. You'd probably use some sort of map with some factory functions. Of course, that's exactly what we did. But this just shows what's going on for our purposes. So if it's a freight bond forward, we can deserialize as that. Just want to point out that we're treating those curves differently because the data is not for the actual curve. It's the name of the curve. So we'll pull that out down here and then recursively call back to deserialize to load, for example, a fitted bond discount curve instead. So far, so good. Let's have a look at the deserialize as method. It's a template. So we create whatever type we're getting back here. Make shared, remember it's a shared pointer. Forward on to deserialize into, so let's have a look at those. That's these functions up here. The first one, fitted bond discount curve. Remember that's that nice simple one. It just has some data members. I'm not deserializing all of them, just enough to show what's going on. And this insertion operator overload, that's what the deserializer type's giving us. So that's it, really. For most of this, we're just deserializing the data and returning it. Except when we get to those dependencies. So if we look at the deserializer for forward, our two curve objects, well, they need separate loads. So here, we're just going to recursively call right the way back to our repo. And you can see we've had to thread the repo all the way down, pass it down all these levels, just so we can go all the way back up again. So we've got some really tight coupling here. The repo knows about the deserializing code. The deserializing code knows about the repo. They can't work without each other. But it does keep this flow nice and simple. We just do everything in one go, and we're done. Because that's really all there is to it. And if we run that, you can see down the bottom, we completed in 122 milliseconds. I did say, milliseconds is accurate enough. Why does it take so long? The bit I didn't show you is the load as JSON method. Now we're using the nloman JSON parser. That's just an implementation detail. The interesting bit is this bit I put in here, because in a real-world application, you probably will be calling out to a database across a network, and there's going to be some latency involved. So to simulate that, I've just put this little sleep in for 10 milliseconds, and that's mostly what we're timing. So really, we're timing the round trips. And we've just loaded 10 objects, one at a time. So at least 100 milliseconds just on that. But do we need to load them all individually? Let's go back to our slide for a moment. Remember, this is the object model we're loading. Now, we actually wanted those two fixed rate bond forwards in the middle. So we know up front, two of the objects together. We could batch load those. Pretty much any data store over a network can allow you to request more than one object at once. So you ask for those two, you get them both back, and then you deserialize them one at a time. But you only pay the cost of one round trip for the two. Once you've got those, as you start deserializing them, rather than going away and resolving those dependencies immediately, you just note what they are, and you sort of have to hold on to this partially built state of the object. But you build up your list of second-level dependencies. There's going to be 6 here, I believe. Or is it 5? 5. Then you've got another batch to do, 5 objects. And then the third-level dependencies of those, the final 4 objects, I believe. That gives us something like this. 3 batches in our case. And as the object graph gets bigger, you'll get more batches, but actually the number of batches will grow at quite a slow rate. So you'll typically have 4 or 5, even for a large object model. So that's much more efficient in terms of that latency. I'm sure you'll agree. So that's what we want to do. How can we change our code base that we've just seen, which is fairly straightforward, to something that will handle this? This is where we get into our problem a little bit more. So let's go back to the code and look at a second stab at this repository. So main, as I say, it's exactly the same as before, but let's have a look at repo, because now we've got 2 additional members. It's hard to read. So to load, that's our set of IDs that we're going to batch load, the things to load, literally. So as we go through, we're going to build that up, and then we'll load them all in one go. And as I say, as you're going, because some things are not going to be built yet until the dependencies come in, we need to track those. So we put that in the incomplete tasks vector. So that's what those are for. We'll look at what build task is in a moment. We've got a couple of extra helpers. We'll see those as we go. Let's go back to load and build objects. This looks a bit more complex than the last time. And in fact, even more of it's put into the helpers. But let's go through this. So we'll pass the IDs in as before. But now, because we are loading batches, we need to populate our to load vector first. And that's actually all this first line is really doing. We're just iterating our IDs and calling require object on them. And that just looks it up in the cache. If it's there, returns it. Otherwise, adds it to the to load vector. So by the end of that for each, we'll have all the IDs in to load. Then we're going to go into this weird double loop. Now, the reason why there's 2 loops here, in fact, we're not really making use of it in this example. I might mention it in a moment. This inner loop is the interesting one. So while there are objects to load, we're going to go through this loop, which of course there will be the first time. Then we're going to deserialize all. So now it's a batch load operation, so we'll do that all together. We'll come back to that in a moment. But once they've all been loaded, maybe not completely built, but loaded, we can clear our to load vector. Okay? Now what we're getting back now are not objects, because they may be partially built. So that's what these build tasks are for. They're the things that are still being built, the tasks to build the object. So we'll iterate through those and try to resolve the dependencies on each one. Because if we already have the dependencies, we can resolve them there and then. But if not, then we put that task on our incomplete tasks vector to come back to later. Okay, so we'll keep going around, and eventually we'll have loaded all those leaf objects. They will immediately resolve. But then we can start resolving the things that are dependent on them. So we'll drop out of that loop and go into this loop, where we're going to go through the incomplete tasks backwards, because we want to start with the least dependent objects and work our way back up to the most dependent. And we're doing it by index, just so we can do this arrays. Now, why do we need to arrays? Because hopefully we should resolve all of them. And in fact, we will in this example. But in the more general case, once we've loaded the first level of dependencies, that object may think, oh, I've got some more dependencies I need. And so you may actually have a multi-stage build. We're not going to go into that. That complicates things a bit. But that is why we have that outer loop as well. So we have to check to load again. But other than that, we should be done. So all that remains is to go through our IDs, look them up in the cache, and populate our output vector. That's all that last section is for. So it wasn't quite as bad as it looked at the start, but there's a couple of things we skipped over. Let's have a look quickly at resolve dependencies first of all. So that's another big function. So we are going to ask the task for its dependencies, so we can iterate those. And then we'll check whether each dependency is met, because maybe we already had it a previous time round. But if not, then remember that require object we looked at earlier, looks it up in the cache. And if it's got it, it returns it immediately. Otherwise, it puts it into the toLoad vector. So we'll either track dependencies we still need, or we'll get them here, and we can supply them. And that just wires it back up into the object. Otherwise, we have unmet dependencies. So after the loop, we'll come in here. If we don't have any unmet dependencies, we're now complete. We can put this object in the cache. So that's great. So really, that's all resolve dependencies is doing. Hopefully, that's straightforward. And I'm moving through quite quickly, so we do have a lot to get through. We will see some of this again. OK, the other thing I didn't cover is deserialize all. Let's say this is now a batch deserializer, so we're going to iterate through the IDs. We know how many tasks we want up front, because it's the same as the number of IDs. We've got a load as JSON as before, deserializer, that's not changed. But then we call this build named object. If we look in there, this looks very similar to our previous deserialize function. We've got our big type switch, forwarding on to build functions. Just a couple of things to note here. First of all, we haven't had to thread the repo through here. The repo is completely out of it now. We're completely separated from it. So we've got much nicer separation of concerns already. And the other thing is, we're treating those curves the same way as all the other objects. We're not having to do this recursive bit here. Let's have a look at the builder for fitted bond discount curve. Remember, it's a simple one. So very similar to before, we create the object up front, deserialize it, and return it. Actually, it looks exactly the same, except that we're returning an object here, but the return type is build task. And that's because in this case, yes, we've got a complete object up front. And build task has a conversion constructor from object. So that's fine, but that's a special case. The general case would be something like fixed rate bond forward. Now we have this dependencies object. We need to track our dependencies. So we create dependencies up front and call require for each of our dependencies. Two of them are actually in that build into. We won't go in there. We'll just look at this one. So require takes the field that needs to be populated. So remember we saw earlier supply dependency. That's just going to set that field. Just captures a lambda internally. And the name of the field on this object that's going to tell us what the dependency is, internally the deserializer will pull it out. So in fact, if we do look into build into, you can see there's a couple more dependencies being captured there as well. But after that, we don't have a complete object. So we'll create our build task, and then we're going to call continue with dependencies on it. This is going to capture the dependencies and a lambda, which is our continuation. So fairly standard callbacks, really. Once you've got this thing for me, call me back. Here's the lambda. But this is really a continuation of the same builder function, if you think of it that way. Because it is a lambda, we've had to move any interesting state in, which in this case is just the object we're building. If we had anything else, we'd move it in as well, or copy it in. And that's it. In this case, at the end, we return the finally built object. It's possible we may have multi-stages, we may have more lambdas within lambdas. We've just got the one level here. So hopefully you're still following this. This is nothing groundbreaking yet. We will look at the curve one as well, because that gets a bit more complex. Because our actual dependency is the object we want. There's nowhere to put it. We don't have an object that we're going to put it into. If we put this curve that we want to build on the stack, we would lose that when we leave the function. So we're putting it in this curve holder, which is just there so we can create that on the heap here, and then move that into our lambda down here. And finally, pull out the curve and return that at the end. So it's just a slightly different approach. You can see it's a fair bit more complex to work around the lifetime issues here. But otherwise, this is much the same as the other one with dependencies we looked at. OK, this is a lot more complex than our serial example. And As I say, I've had to move through it quite quickly, so I may have lost you in places already. But it's not that bad. It works. Let's run it and see that now it's taking, it does vary a lot, but usually around 40 milliseconds. So it's a bit more variability today. It's in demo mode, which is about a third of what it was running in our serial case. So we've got exactly the sort of speed up that we expected just by reducing the number of batches down to 3 instead of 10. So this may be worth it, may be worth the extra complexity. So how are we doing for time? 26 minutes. OK, we haven't got to coroutines yet. I think we've just got time to see how deep the rabbit hole goes. Right, so what we've just seen here is an initial attempt at batching our loads using lambdas and continuations. But it's very specific to our problem. And it's just a minimum viable version of this that I put together for the talk. A real-world version would be much more complicated, as in fact the one that I worked on years ago was. If we want to make it a bit more production-ready and a bit more general, so not just for our case here, but configuration points for other things as well, how might we do that? Let's take a stab at that. So I'm actually going to go back to the slides. I've got some slides to show you that in. Right. So we looked at this builder for fitted bond discount curve. It's a nice simple one, because we just return the object at the end. So we'll start there. And remember, we're returning the build task, but actually the return value is the object. Because we don't have any dependencies here, and we can return that object directly, there's no lambdas, no continuations. But in the more general case, we may want to always put this into a lambda up front, so we can decide from the outside whether we immediately execute that code or whether we defer it. In other words, whether we initially suspend or immediately execute that code. So let's put that in a lambda. We'll introduce our build task, and we use that continue with task method. So no dependencies here, nothing to wait for. And now the return task looks a bit more natural, and we've got return object within the lambda. You can actually say that maybe it's a bit clearer. But we need some way to configure that as well. So somewhere outside, we're going to have something somewhere we can say, should we initially suspend or not? Let's write a function like this. Can return a ball, that's going to be fine for now. In this case, we return false. We don't want to initially suspend, we want to execute it immediately. If we return true, we'd hold on to the lambda and wait for something to say, now you can resume. Straightforward, hopefully. In fact, we probably know at compile time if we want to do this or not. And so rather than a ball, maybe we'd return a different type for that. We're not going to do it right here, but we'll see that in action a bit later. OK, so where are we going to put that? Well, we have our build task. That's the thing that's running all this continuation stuff. So we probably want to put it in there. But what we actually did, I didn't show you this before. We put all the state for build task into a struct we call data here. That's all the state for our build task. And really, I did that before, just because it's convenient to be able to give this object move semantics, because we just got a unique pointer to our data. We didn't really strictly need to do that, but we've done it. So we have this data struct. So we should probably put it in there, because this is everything to do with how we manage our set of continuations. Now, having a look in there, we've got the ID, we've got our set of dependencies, we've got the object that we're building, and we've got this continuation. Now, the first three things, they're very specific to the problem at hand. They're all to do with this dependency building thing that we're doing. The continuation is a much more general part of the infrastructure. It's a different type of thing. The continuation, by the way, is just the lambda that we're going to call next. So maybe we should treat that a little bit differently and move it out of our data type, put it somewhere else. And if we put in that somewhere else, maybe we'll think about some other things that we put there as well. So If we've got any other sort of general continuation management state, like we'll actually have an awaiter, as you'll see, and some other things, continuation manager, that all goes up there. But that also needs to know the type of our data struct so it can interact with it. And maybe we'll call this thing, bear with me here, the frame. So we've got this frame that has all of the generalized continuation management state, including our continuation lambda. And then our, we'll call it data struct, is just the bits that relate to our particular usage of this. Okay? Separation of concerns again. I'll claim that. Now, this frame stuff is very low level. We don't really want to be interacting with that directly. We don't want visibility of it. So maybe we'll just push it off an extra level of indirection, and we'll interact with it via something we're going to call a frame handle. So we'll get a handle, and we can ask it to perform operations, but we never see the definition of it. We don't need to. But the frame handle, or the frame itself, and therefore the frame handle, needs to know about our data type. So it has to be a template. Okay. By the way, if you have seen other coroutines talks before, some of this may already be starting to sound familiar, but bear with me. Okay, so we've got this frame. Where do we create that? Well, we're going to need to create it within, in our case, our builder functions. So the first thing we do is we create a frame. So I've got this make frame helper. Again, you give it our data type. And then you pass that, our initial lambda, our initial continuation, if you like. We've also got this co thing. I don't know if you can see that up there. We'll come back to that in a moment. So we've got an initial lambda. We give that to the frame. It's all much more generalized now. What do we return at the end, though? We're creating a frame. We need a build task. We seem to have lost that. So let's take a step back, because the build task needs the frame handle, but we also have our data block. Taking a little peek in the definition of frame, you can see it's got a base class, happens to have virtual methods in. That will become significant. But the first member is data. So it's holding our data type by value, right within the frame. So we haven't had any extra heap allocations for that, so that's good. But that means if we have a pointer to our data, well, we can sort of work backwards and get a pointer to the frame. It's not particularly nice, and here's a stab at it that has some undefined behavior in it. You shouldn't do this. It happens to work on my machine. You would need at least a std launder in there somewhere. That's not the purpose of this talk. Purpose of showing you this is to show you it can be done. It's just a bit messy. We're just finding out the offset and working back. But that means that given a pointer to a data type, we can get back the frame that holds it. So in our data type, we can add this method, get return object. So we already know the pointer to data, it's us, this. We can call that handle from data to get back, well, wraps the frame in the handle. And then we can pass the handle to the build task, and we can return that. I know it seems a bit torturous, but each one of these steps has a reason. And then this is where we end up. Okay, if you didn't follow that, don't worry. But that's what we're doing. That means that at the end of our builder function, we can now say the frame's data dot get return object, and that's what gets returned. And that means that our build task is going to have to manage the lifetime of the frame as well, because we sort of lost it at this point. We've only got the handle to it in the build task, and the handle is not an RAI object. You have to explicitly destroy it, so we'll need to call that as well. It's our responsibility. Okay, now while we're here, we'll go back to the data type. Here's another thing we can add. Oh, actually, no, I should go back. The other thing that's still a bit odd is that return obj at the end of the lambda. Because if we're generalizing this a bit more, we always want to be returning the next continuation. So instead of returning the object, we want to call something with it. And indirectly, we're going to end up calling this function, this method, a return value on our data type, because we want to gain access to the object so we can store it away. That's exactly what we're doing here. Passed in by our value reference and moved into our local instance. So we're going to need something that's going to let us call it, and then we'll call this for us. So that co object that's passed into the Lambda, I'm actually calling it a continuation manager, just co for short. Yep, bear with me. So I know it's stretching it a bit now. So we can say co.return. Well, I'd like to say return, but that's a keyword, so it's return underscore, but just forget that's there. And we pass out the object, and our configuration manager will then say, oh, okay, I'll pass this on to the data type, return value. Okay. Won't bother showing that bit, it's pretty trivial. Okay, but that was a simple case where we don't have any dependencies, no continuations. Let's look at the more complex one. Okay, we've got our continuation manager again, co. This time, we have our dependencies, and then rather than returning the continue with dependencies, we say co.await. And we give it the dependencies that we're waiting on. And after that, we say dot then, and if you can read that bit under there. And then there's a continuation lambda. And in there, we have co.return. So you can see it's actually starting to become a little bit more consistent. We're just using this continuation manager to do all of our instrumentation. Quite nice. OK. What happens when you call co.await, though? That's a little bit more involved. It's much the same as the continue with dependencies that we saw earlier. We didn't look at the implementation of it. But continue with dependencies was in our code before, but now we've moved it into this low-level infrastructure code that we don't get to see. So we've actually lost an ability to observe what's going on and maybe do something else with it. So what the infrastructure will do, well, there's three things it can do. I've chosen one of them here. It calls this await transform method of our data type with the thing that we're waiting for. And then in there, we can create what we call an awaiter, a dependency awaiter in this case. And we also have a chance to squirrel away the dependencies. Now, the dependency awaiter in our case is almost just an observer. We've got one thing that we do pass in, this should suspend. Because we don't need to suspend if we've already got our dependencies or we don't have any dependencies. So that's what we pass in as should suspend. So when the infrastructure asks the awaiter, are you ready? Then it can tell whether it had any dependencies or not. Other than that, it gets called back with suspend when the whole thing is suspended. So we can do something there. We're just logging, but we could do something else. We actually get a frame handle there, which you'll see is actually a type erased one, which is quite convenient. And again, you can be called back on resume. When you're resuming, you could do something else there. We're just logging. But that's what the awaiter looks like here. OK. You can tell I'm stretching the analogy a bit, but I'm also trying to show you the reasons why we're building up to these things. So let's actually drop the charade and have a look at coroutines. And then we'll look at the version of this code with coroutines. So these are the different types involved. They may look a little bit familiar at this point. We've got this coroutine frame. We're talking about the frame. It's essentially the same thing, managed for you by the infrastructure, of course. We've got a coroutine handle, like our frame handle, which comes in both the typed and the type erased versions. So level of indirection there. But we still have to manage the lifetime. But that gives us access to everything in the frame, including the instance of, well, it's called here the promise type, but it's what we were calling data before. That was our internal state for our build task that we moved off there. I didn't call it promise type there because a lot of people find that a bit confusing, especially if you're thinking of futures and promises. But it's not really to do with that. It's really just the internal state of your task or generator. That's what promise type is. And also gives you that set of methods that we'll look at in a second that gets called by the infrastructure for different purposes. We have our task or generator type. In our case, it was a task type, build task. So this is all on the user-provided side, and optionally an awaiter type, our dependency awaiter. These are all the things that participate in the coroutines ecosystem. Now there's some other types as well, which I mentioned briefly. Suspend always and suspend never. Now they're actually specific types of awaiter. We call them trivially awaitable types. All they do is just tell whether you should suspend or not. Remember we had that Boolean before. But now we've got separate types for them potentially. And because these are known types, the coroutines infrastructure can actually make that decision at compile time, which is nice. So you'll very often see these types being used, and you'll see them in a moment. There's a couple of other types as well, which I'm not going to talk about now. They're a little bit more advanced. Coroutine traits and no-op coroutine promise. But just for completeness, I'll put that there. Now the task and the awaiter types, they get given and they can optionally hang on to coroutine handles. So we have those relationships there. But it's the coroutine handle that knows about the promise type, or the instance of the promise type. The consequence of that is if you're in a task and you need access to that internal state, even if you actually got the definition of the type there with you, you've got to ask the coroutine to give you the promise instance. So you'll see that dance done a few times. Similar with the awaiter. There's some other consequences of this model, which go beyond what I showed you with the lambdas example. So with the lambdas example, we created the frame on the heap up front, but then all we did was we put the initial lambda in there, which didn't really have any state. But then internally to the lambda, you've got local variables. And remember, you had to move them into the following lambda if you wanted to keep using them. And then there was that one with the curve where we had to create another object on the heap just so that it had a stable address that we could refer to later. That's all nasty stuff to reason about. But with a real coroutine, it can actually do things a little bit more intelligently. And in fact, the coroutine frame is created usually on the heap. Think of it as always on the heap. And all of the local variables are also allocated there as well. So if you've got, say, our curve type, we'll see this in a bit, a curve object on there, then it's got a stable address that persists after being suspended and resumed. So that's really nice. And all of the promise type is in there as well. So it's all in a single block of memory. Oh yeah, and as we said, it's usually the responsibility of the task to manage the lifetime of the coroutine frame by the handle. There's a special case where the coroutine can manage it itself, but we won't get into that. Okay, I'm actually going to jump back to the code example now. That's there, yeah. Jump ahead to this one. So this is now the same example, but with coroutines. We finally got to showing you coroutines in practice. Main is exactly the same. If I look in repo, that's actually exactly the same. If I look in load and build objects, okay, this is almost exactly the same. There is one difference, which I will find here. So our loop where we've got the build tasks returned, and we need to iterate the build tasks. We're actually doing something slightly different here, and I'm going to come back to why in a moment. But let's just assume the rest of it's the same for the moment. So where's the difference? Let's have a look at our builders, and we'll see there. If we go to the simple one first, fitted bond discount curve. So we are returning a build task, as before, but everything else is basically the same, except we've got co_return instead of co.return. Yeah, I didn't fool you. And in fact, I think it might even be easier to show you this just as a diff. I'll need to change the font size in a moment. So here I think we can see it a bit more clearly. Is that big enough? Can you see that further back? I'm not seeing any hands, which probably means you can't. But I'll talk you through it anyway. I don't think the colors come out very well on this screen. So at the start, in our previous example, we created a frame and we had all of that messy, creating a lambda and moving stuff in the continuation manager. We don't have any of that now. Of course, that's all generated by the compiler behind the scenes. And it obviously doesn't look exactly like that, but the equivalent. And the same with the last line, returning the build task by calling getReturn object. Everything in the middle is basically unchanged, except again for our call to co.await, which was very messy before. Now it's very clear. Co_await, and in this case, dependencies.resolve. I've actually chosen one of the other options here. Said there were 3 options for managing awaiters. We'll see what I mean by that in a moment. So this is a lot simpler. Now, what I'm going to show you next is not quite as simple. But I want you to bear in mind that in this code base, we've got our infrastructure code once, and then dozens or hundreds of these builders. So having the builders be nice and clean and simple is really the thing here. And I also want to show you the curve builder here. And so hopefully you can at least see big blocks of red where we don't have code anymore. We had before. So as well as the make frame, we have that curve holder and creating the shared instance of it. Simply so we had the stable address. I talked about this before. Now we just create the curve effectively on the stack, set it as a dependency, and use it at the end. So this is drastically simpler. And the reason I wanted to show you this is because this is one of the nice things you can take advantage of when you know how this all works, is just relying on stable addresses of things while the coroutine is in progress. Whereas you couldn't do that with the continuation passing version. And we will see another way that pays off in a while as well. OK, and while we're here, let's see if we can use this to see the difference with the build task. So in fact, the first big difference, that big block of red up there, let's make that bigger, sorry. Our dependency awaiter, and we do still have one, I've just moved it somewhere else. It looks almost identical. So that hasn't actually changed. Most of what's changed are the names, not just to protect the innocent. So our embedded data struct has become promise type here. We've got from promise instead of from data, if you can read that. This bit's interesting. Let's try and zoom in a bit more. We previously had a vector of dependencies because we moved our dependencies in. Here, now with coroutines on the right-hand side, we can do a span of dependencies because our vector still lives on the stack of the coroutine. Again, because objects in the coroutine are stable between suspension points, we can do that now. We couldn't before. So there's lots of opportunities for optimizing things that way. The other difference here, our initial suspend returned a bool before. Now it's returning suspend never as a type. And we have final suspend as well. I didn't use that before, but we also get to control whether the coroutine suspends at the end of its execution. And spoiler, unless you know otherwise, you should always do suspend always, because otherwise the coroutine has to clear itself up, and it gets a bit tricky. But there are cases where you need to do that. And we have this unhandled exception. We didn't do that before, but if an exception is thrown while the coroutine is in progress and there's no obvious way for that to be handled, then it actually comes through to here. You get a chance to catch it in the build task level. Well, we didn't do that before. And then here we have our await transform. We already saw that before. I don't have the equivalent in this build task. We could do, and it would look almost exactly the same. So we could do it that way. But the more common way is what I've done here. It's not in here, actually. It's in. Where's it gone? Have I lost a file? It's on this side, sorry, yes. So in dependencies itself, I've added a method, resolve. Remember we said await, co-await, dependencies.resolve. That calls through to here. It's in the CPP file. Sorry, let's go back to the code. I think that's going to be easier at this point. Here we go. It's dependencies resolve that returns the awaiter. So if you control the object you want to await on, this is usually the cleaner way to do it. You either have a method on there that returns the awaiter directly, or there's an operator co-await. You can do it that way. So you can do that outside, but you still control it. I'm not going to show you all the variations, but just be aware there's a few different ways to do it. And that means you can await on things that you don't control as well, using the await transform method that I showed you before. So for example, people have created awaiters for stood optional. So you can actually fake a monadic operation on optional using that. And then if I go back to too far up. Back to the header file, there's the awaiter. It does almost exactly the same as before, just in a different place. So there was not that much difference between our final continuations version and the actual coroutines version, and most of the differences are actually removing code. So contrary to what I said at the start, that you can end up with a solution to a problem that seems much more complex, we've actually simplified things here now by using coroutines, especially in the code that you use the most. But we still had to write a fair bit of infrastructure in the build task. And this gets back to the thing I said I'd come back to, the difference in the repo here. Instead of just iterating over our build task vector we had before, we're now doing has value and .next. And the reason is I've introduced another coroutine here. I didn't have to, but just to demonstrate it. Deserialize all. If I go into that briefly. Come on. It returns this loaded object generator. This is another coroutine, a simpler type of coroutine. And if we come down here, you'll see we co-yield each build task. So rather than building up a vector of build tasks in advance and returning that, we iterate through and return each yield each build task as we go. So this is a bit like co-await, but it's a way of getting values back to the caller in a loop, usually. And that's why we call this a generator. And if I show you loaded object generator, it's got all the same usual suspects, some different names there. But instead of return value, we have yield value and return void. So yield value is what gets called for each of those co-yields. Again, we're just squirreling that away in our promise type. And later, we have this current task method on the build task in the generator type that returns the current build task. We also have has value that checks if we have one or if we've finished iterating, and next to move to the next one, which actually will end up resuming the coroutine. So you're going via one coroutine to get to another one. Now actually, apart from the naming, there's not really anything about this that is specific to our problem. So we can easily write a more general purpose generator. And if we're doing that, we might want to go a little bit further. And rather than having this slightly different interface, you can see how we could add some iterators to this and have a range-based interface. And then our repo code, repo code will be exactly the same as it was before, but now with a generator instead of a vector. So I'm not going to go on to show that, but I will say that C++23 now has stood generator, or will have, which does exactly that, which means all of this code I'm showing on this this screen here just disappears. And if all you need is a generator, there's almost no additional code that you'll need to write. You can just add co-yield and a std generator, and everything will just work as you would expect. If you've seen other coroutines talks, you've probably seen that in action already. That's very often the first example because it's nice and simple. Well, I left that for the end, just to give you something nice to think about. So, I think I just have one more slide to get to. There we go. Here we go, yeah. Oh, sorry, I went back too far. Right, so I just wanted to recap the players in this, now that we've seen them all, not just in action, but how we got there as well. So in our code, we have a task or generator type. This is, you can think of this as like the remote control for the coroutine. It's our interface to it and where we have our intermediate state. We control it. So if it's a generator, from C++23, you may not even need to write this. It has the definition of the promise type, usually. It doesn't have the instance. That's owned by the coroutine itself. But you usually define it either within your task type, or you can use a type alias, or there's another way to define that separately, but that's how you would usually do it. And you'll usually hold the coroutine handle, because you need to do lifetime management. Again, there are cases where the coroutine can do it itself. That's an advanced topic. So the promise type has these methods. I think we looked at all of them now. Usually, you will see these all up front and be overwhelmed and think, why do we need all this? But hopefully, I've given you a gentler route in. So we've got a way to get our task type given an instance of the promise type, which is on the heap. Initial suspend and final suspend controls whether the initial block of code in the coroutine runs or not, and whether it leaves in a suspended state. And you can usually say that at compile time. You can do it at runtime as well if you need. Return value or return void. You implement one or the other of those depending on whether your coroutine has a co-return that returns a value or not. Hopefully that's fairly straightforward. And unhandled exception gives you a place to catch those exceptions as they come through and do something about it. Very often you'll just see that doing nothing or terminating. And then the awaiter. We didn't dig into this quite as much as we might do in a talk more about that subject. I just showed you it working mostly as an observer, but actually you can do a lot more with an awaiter. Has these three methods, but you can actually say which coroutine suspends and resumes, which allows you to transfer the runtime to a different coroutine as you're going. Something called symmetric transfer, which I'm not going to go into now, but look that up if you're interested. And in fact, I think I've come in just about on time. I've got a link up here. Take a note of this, because I'm going to put all the references and sets of other talks on there. It's not there yet. This is a promise. I will get to this later today. Make a note of the URL. I'll put it there. I'll put it on the Discord as well. But I haven't had a chance to put my usual references slide up. But other than that, thank you. This has been C++ coroutines from scratch.